and we are ready to go. Glad you guys are here. Noah and Chris, welcome to the Greenhouse Tech Talk stage.
Hey guys, I'm Noah, and this is Chris. We're from the Core Protocol team here at Algorand, and today we're going to talk to you about Core Protocol performance. So blockchain performance is a highly touted area. While first and second generation blockchains offer a lot of promise, they become difficult to use if only a few people can afford to use them at once. Over the past few years, we've seen a rise in the number of Layer 1 and Layer 2 blockchains competing to solve these scalability issues. With so many options out there, it's been hard for projects to choose which chain to build on when so many of them claim to safely solve or reach these scalability issues. Sorry, technical problem. As our industry starts to move into the value creation phase, we're starting to see consumer-grade applications solving real-world problems built with blockchain technology. These teams want to know what security or decentralization trade-offs are being made behind the scenes, as it can directly impact the user experience. So where does Algorand fit into this picture? Well, a few years ago, Algorand launched with a novel pure proof-of-stake consensus mechanism. Pure proof-of-stake is hyper-focused on decentralization and security, which impacts how we approach scalability. So there's a lot to cover here, but I'll call out a few highlights. First, Algorand uses a verifiable random function, or VRF, which randomly samples consensus members to propose new blocks and to form voting committees that validate these block proposals. Since the VRF uses random sampling, Algorand fixes each committee to a maximum size, regardless of how many online participants there are. By fixing this maximum committee size, the network can scale up to handle millions of participating accounts without restricting performance. Second, Algorand has a low barrier to entry. People can participate in securing the network with as little as one algo, which allows it to become more decentralized over time. And third, Algorand is one of the first movers on post-quantum security. By launching state proofs, the Algorand blockchain now uses post-quantum cryptography to attest the state of the blockchain, allowing it to protect blockchain history from quantum computer attacks. What this all means is that the blockchain is well protected from risks like downtime, censorship, deplatforming, economic attacks, and lots of other nasty stuff that comes from centralized trust assumptions. For example, since Algorand uses random lotteries to select block proposers, the network needs to route traffic to all online participants, which means consensus votes, transactions, etc., rather than filtering it to one specific node. This makes it really hard to target or bias individual proposers or voting committee members because nobody knows who they are until after their job has already been completed. This is in contrast to many other blockchains who know who block proposers will be in advance, which allows them to achieve large performance gains by routing traffic to a specific set of nodes. However, this comes at the cost of reducing decentralization and increasing the associated risks that come with it. So Algorand has made some design choices that boost decentralization and security, but restrict some of the ways that we can boost performance. So how do we scale it up? Well, there's a bunch of different techniques. First, you can increase the block size, because bigger blocks means there's more space to add more transactions inside of them. Second, you can reduce block latency, because producing blocks more frequently means you can settle more transactions on chain per second. Third, you can parallelize block production and verification. Now, this one's pretty cool, and it's something experimental that we're trying to play with right now. But if you think of each round, every round, you have a block that's assembled with transactions inside of them. You can think of this block as a train that's leaving the station. The block size determines how many transactions or how many seats there are on this train for transactions to fit on board, and the latency is how fast that train goes or how long it takes for that trip to be completed. Using this train analogy, currently only one train can leave the station every round, which is currently 3.7 seconds, but as I mentioned, that round time's continuing to come down. Well, what if in addition to this, we also added more tracks to this train station, so that rather than having one train depart every 3.7 seconds, you could have multiple trains departing within this 3.7 second interval. This would allow you to greatly boost your TPS and also, very importantly, reduce transaction latency, which means shorter queue lines, nobody likes waiting, you can have a transaction get on board a lot faster. Now, there's a bunch of other cool things that we're experimenting with, but I'll leave Chris to talk about some of those interesting technical details. So, what did we accomplish in the past year? Well, we delivered a bunch of optimizations under the hood that allowed us to 5x our performance to 6,000 transactions per second. First, we optimized the database for higher throughput so that, I'm sorry, just lost my train of thought. Higher throughput by making it faster to read and write to disk, especially when accounts have a lot of assets or have opted into a lot of applications. Previously, accounts were limited to create up to 1,000 assets or opt into 50 applications. Well, this new unlimited apps and assets feature removed a big blocker for higher TPS, with an added benefit to both the creator and DeFi economies. Creators can now mint as many assets as they want, and people can use as many DeFi apps as they'd like. Second, we delivered a bunch of optimizations on how we score account data. By significantly reducing the memory pressure on each AlgoD node, we were able to safely increase our maximum block size. So coming back to this train analogy, there's more seats on that train. And third, we reduced round times, so blocks are produced and verified more frequently, providing a better user experience and boosting TPS, which makes that train go faster. So you might be wondering, what comes next? Well, we're going to continue focusing on faster rounds, so we continue to make that trip faster. As Paul talked about earlier, we've got instant finality, so once that train reaches the station, there's no question on if those transactions on board are legitimate or not. Making applications much snappier and making it feel even more like a Web 2 experience. So this 6K TPS milestone is great, but what does this actually provide? Does this one number cover such a broad area as scalability or performance? Well, our industry has some problems with how we benchmark performance. We're missing a common framework to evaluate blockchains on some of these core protocol properties like performance. Looking at TPS, we have a few issues. First, there's a lack of standardization. So if different blockchains have different definitions for what even constitutes a transaction, how can we try to benchmark transactions per second across the industry? Second, there's a lack of breadth. TPS is a broad metric, capturing how many transactions can be settled on chain per second. But there's many different flavors of transactions. On Algorand, for example, you've got payment transactions, which moves algos from one account to another. You've got asset transfer transactions, which moves NFTs and other ASAs. You've got application calls, which is the bread and butter of smart contracts. And when you look at actual use cases on chain, they may use a mixture of these different types of transactions. So if you're looking at actual user actions that you can accomplish or outcomes per second, you might have a mixture of these different transactions. We can try getting more granular to demonstrate how these different use cases scale rather than some broad metric like TPS. Third, there's a lack of transparency. If people like the numbers they're seeing, how can they actually verify that these numbers are legitimate? And what trade-offs are being made that might expose people to security or decentralization risks? Well, it's very early on this, but we're starting to think about how to create these frameworks to measure blockchain performance and other core protocol properties. This is going to be a collaborative effort, so we're looking for feedback from the community and builders to see what types of benchmarks and standards you think would be helpful. So if you find this interesting or have some cool ideas, please come talk to us after the talk, and we'd love to chat. That's it for my part, and I'm going to turn things over to Chris.
Hi. So I've been asked to talk a little bit about what goes on in a typical round in Algorand, and then how that maps to our priorities on roadmap for performance. And these are really broad categories of work for each of these different phases of what happens in a typical round. And there's a lot of work we're currently working on, or we've already completed, or we're still thinking about or doing research on. So the first thing that happens in a block's round, the round of Algorand, the consensus protocol has these three phases. There's block proposal, there's the soft vote, and then there's the cert vote. And if you've read about the protocol, those are typically the terms you hear. And then in between, there's this idea that we need to make the blocks and then push them out to all the voters and then get them to them in time and then validate the blocks in time for the cert vote. So I'm going to go into each of those different phases and then talk about some of the work we've been doing or are thinking about or have already done on each one. So the first step is block proposal assembly, and this is kind of a race, right? You get the last block was just confirmed, the cert quorum was observed, and now it's a race to just evaluate the transactions you've got ready to go against the state that may have been changed in the last block's confirmation. And so you're at this moment you're both accepting the state that just confirmed from that would have changed the ledger, and then reevaluating transactions against this updated ledger from the previous block. And this is really a great place for benchmarking, optimization, and just focusing on, as blocks get bigger, how can we make it quicker to assemble blocks and get them out to the network as quickly as possible. So this is not at all a complete list of all the types of optimizations you want to do. This is kind of a grab bag of topics that we put together for this discussion. But in general, with larger block sizes, more transactions, block assembly can take more time. And so one of the first optimizations Noah already mentioned is this idea of optimizing the storage and the database that represents the ledger from the point of view of a transaction, so that a transaction's data can be retrieved as quickly as possible. In the last year or so, asset transfers have taken up the majority of transactions on Algorand, and so optimizing for asset transfers, led us to this idea that splitting the resource storage of assets and apps and from their holders and their creators, so that when you transfer an asset, as little state is required both in memory as well as on a disk, or CPU required to copy pieces of information. This led us not only to optimize the storage and the handling of asset data and app data, but also to dereference them from the accounts that are the creators and the holders of the assets and the apps, and then also make it totally unlimited, the number of assets you can hold. Whereas before there was this limit of 1,000 assets and 50 apps you could opt into. And this type of feedback from just what people are doing on chain, is driving the benchmarking and the sort of the profiling we're doing on the types of transactions we want to make faster. And similar to database and storage optimizations on the schema and the ledger, there's also just the evaluation and how much caching we can do from when we first observe a transaction. It comes into the network, nodes evaluate the transaction right away, and then later when it's time to assemble, there are side effects of the first evaluation that can benefit the second one, right? And so anything we can do where when the transaction's first received, this gives us a chance to observe ledger state that may have been touched or read or written as part of transaction processing, or even just validity checks and signature checks that we can use to speed up that second evaluation. And so that's a very large category of caching improvements we could make. CPU optimizations is as general as it sounds. Everything about the way we process transactions and the code we write and the way our systems are built to make it as quickly and use a little CPU work as necessary to handle a transaction and assemble that block as quickly as possible. And then finally, parallel transaction evaluation. That's the idea that two transactions that may not at all affect each other's state, logically should be able to be processed in parallel. And so this is some work we've been thinking about and researching about how to handle transactions and assemble them in parallel when they don't touch each other's state. After a proposal is assembled, of course, you need to get it out to the world, and the most critical path is between the proposers and the set of the soft vote and cert vote committees that are responsible for voting on whether that proposal should be accepted by the network. And so a small detail is that the proposal is split between this small proposal hash and then the proposal payload. And so non-winning proposals are just sort of discarded by the network as they propagate, but the soft vote is basically, as we'll see later, is based on the proposal hash, who's the winner of the proposal, and then the cert vote is based on the proposal payload, whether a payload was actually validated and received and certified by all the validators. And so the proposal propagation problem is sort of two-pronged. There's this small message that needs to get propagated quickly, and then there's larger message that needs to get out to everyone who's watching consensus traffic, whether they're voting or not. And so in this moment, it's drawn as a gradient because everyone's experience of when a proposal arrives is based on their position in the network from the proposer, right? So if you're really far away, either geographically or logically, all these different hops and different paths between you and the proposer would determine your observation of when that proposal arrived. And so that's why there's a big topic here about just network routing and gossip protocol improvements, where we're always looking at how we can more effectively use the gossip network that connects everyone on Algorand to get as quickly as possible this consensus traffic, and especially the proposals from proposers to voters and observers. And so one simple technique is just compression, right? We've got these bigger blocks all the time. We want to have bigger blocks, and so compressing the proposals and having effective but also performant compression to support the slower bandwidth times. And the network is there are constraints between any 2 points in the world that the network is the speed of light and bandwidth between ISPs and things that you can't control for as much as what you can do on a local node. And so there's all sorts of work we're doing on how to optimize the routing and the payload sizes. And then transaction deduplication refers to this idea that if I'm going to send you a proposal and you've already seen some of those transactions, I don't necessarily have to tell you them all because we have the shared knowledge of the same transaction. And so there's this opportunity for even better compression where we both have observed the same transaction, and so a proposal I send you might only reference those transactions in a smaller way than they would appear originally in the proposal. And then finally, this is something we're working on right now, is this idea of framing a block proposal. As we see block proposals get bigger and bigger, if you could split them into smaller verifiable frames, and that sort of optimizes the forwarding of all these different paths that are available between you and the receiver of a proposal. So if I'm getting the same proposal for 2 or more sources, I shouldn't have to sort of duplicate and have all this wasted bandwidth where I'm receiving the same data from 2 different channels, right? I should probably be able to make better use of the bandwidth so to get unique chunks or frames of the proposal from the multiple peers I'm connected to, and sort of speed up the transmission and the forwarding of proposals. And there's a whole bunch of optimizations we could make once we start to split up proposals into smaller verifiable frames. And then after proposals have been delivered, there's this whole concern of making sure they're valid, right? And so a soft vote is, again, not based on the validity of a block, but rather on the lowest credential, the winning VRF credential. But the cert vote requires that a block's been validated. You're not going to certify a block that hasn't been validated. So validation is very, very similar to assembly. You're just evaluating transactions and a block header. You want to make sure that everything is correct. And so all the optimizations we already discussed related to assembly do apply here for validation as well, with the extra benefit that a little more time has passed since the last round completed, so you have a little more space to make use of any information that might have happened from then. This is one big change. We changed the consensus protocol, and we changed our ED 25519 signature validation rules to support batch verification. And this was a consensus protocol change that was pushed sometime this year to support just this case, right? You get a whole bunch of transactions you may never have seen before, and you need to check all their signatures in a batch. And so this is a speed up of roughly 2.5x, where you can process them much more quickly as a batch rather than one at a time. And all the other optimizations I discussed for assembly also apply. The idea of transaction evaluation being as fast as it can. Again, if you've seen some of these transactions before, there's opportunities for optimization as well. And then after the proposals are sort of propagating, maybe they haven't all fully gotten to everyone, or they haven't been fully validated, this idea of the soft vote, also known as the filtering vote, or the filter vote if you've looked at some of the specs, is this process of filtering down 20 proposers on average to just one winner, all right? And then everyone votes on who they observed was the lowest credential. There's this winning VRF credential hash that signifies you're the winner of the proposal lottery. And so the soft vote is the only fixed timeout, or in this diagram, is the only fixed timeout event that occurs during a round. Is every X seconds since the beginning of the round, the soft vote fires and everyone votes for who they observed was the winner. So our goal is to make sure that by the time that happens, all this information is in place to make sure that everyone votes correctly, as well as we try to squeeze round times closer and closer together, have faster and faster rounds, we need to have a higher throughput of votes that we can process, right? And so we don't typically think of consensus traffic as a huge bottleneck or a very big draw, but as we make more rounds, you need more votes, right? And so having all the optimizations we can make on assembly, on agreement traffic, consensus traffic, so that we're always keeping up with the demands of the higher throughput from faster rounds is a project that we've continually been working on. And so this continually improving in terms of the batch verification. Every vote is actually 3 votes, so even just a little batch verification there speeds that up. Again, all the idea of network routing and priorities for consensus traffic and the gossip protocol improvements really pay off here as well. And then, one thing we've been doing is we've been reducing the soft vote timeout, and that creates faster rounds. The more we get towards comfort about the effects of changes on the network and how we think mainnet can handle it, we've been reducing the soft vote timeout as well. And then there's this idea of a dynamic soft vote timeout that has come up in research, where you are adjusting according to the network conditions. As in a rapidly changing network environment, there are occasionally possibilities that huge tier 1 disruptions occur, and you might want to have that be reacted to by the soft vote timeout. And so this is something we've also been thinking about and working on. And so the cert vote, final step, last slide, and is the process by which everyone finally says, okay, this is the winning block. And so the proposal that received the quorum of soft votes is the winner of the cert vote. And so there's this whole separate committee of a couple thousand people who vote on the first quorum, but with the extra requirement that they've also all validated the block, or else they won't make a cert vote. And so here's another opportunity where being able to process all the soft votes really quickly so you can turn around the cert vote is important, and that's where batch verification might come in handy. Again, all the network routing improvements we discussed. And then also the cert vote, you're basically, the dead time in a cert vote is just issuing a cert vote and everyone observing a cert vote quorum. So it's kind of this all pairs broadcast situation where you're just sitting around waiting for the entire network to exchange the cert vote and observe that a cert vote quorum has been achieved. And so you could just get started making the next block, right? If you're reasonably sure that the block you just voted for is going to be the winner, why wait until it gets confirmed to start the work on the next block? And so this is something we're excited about called speculative assembly. It's this idea that you might benefit or get a little more, squeeze a little more assembly time out of kicking off that next block before the first one, before the current round confirms. So that's why I've drawn, right after round n+1, this idea of block proposal assembly being able to start maybe a little bit earlier. Of course, if the block you voted on didn't win, you should not, that's not a proposal you should send anyone, right? But the idea that you can get started a little earlier is something that's related to pipelining, which is another technique of kind of taking advantage of parallelization of the rounds, right? So speculating on n+1 leads you to think, well, if I've already pretty sure that what n+1 is going to be, maybe I should speculate on n+2 and so on and so forth. And so the idea of pipelining is, speculative assembly is sort of like the first step towards this idea of this more general concept of pipelining. That's all I got, but I hope this was illuminating for some of the parts of the consensus protocol that might have been. Any questions? I already see one. Thank you. Right. Yeah, so this is part of the engineering team.
Please repeat the question.
Oh, yes.
Maybe
yeah.
I'll let Ann ask it again.
When you make these performance optimizations, how do you then test the network to make sure it worked?
So this is in the theme of the engineering team's process of continual improvement. We're always running benchmarks. We're always running internal test networks, simulating networks of dozens to hundreds of nodes and even 1,000 nodes to make sure that we've got different use cases mapped out to different benchmarks and making sure that different transaction workloads or different node profiles and hardware constraints are all kind of modeled out. And and so this is just sort of something we're always doing and always thinking about, and even small improvements and big improvements are sort of measured against this baseline, or the various baselines that we've worked on.
I have a couple of questions on the consensus protocol. One thing is that is a pure proof of stake, right? And it uses a VRF. So does it prioritize, let's suppose VRF chooses the validator node randomly. Does it give priority to someone with a higher stake? Because VRF will have to choose the node randomly, right? But what if I have the higher stake? Because proof of stake means that if you have the higher stake, you should get the more priority to assemble the blocks and get more rewards, right? So how does that work?
Oh, you're asking how does the VRF interact with the amount of stake you have?
Yeah.
Yeah. So your stake is weighted, right? The stake determines your weight, and so you can think of it as the number of lottery tickets you have is relative to the stake amount you have. So when I said the lowest proposal is the winner, you actually have more than one lottery ticket in that scenario, and so the lowest hash you might have 20 chances to get the lowest proposal hash, whereas someone with less stake than you might have 10 chances to get the lowest proposal hash. And so it's like you've got more raffle tickets, basically, if you've got more stake.
Right. And I think one of in the previous talk there was one of the thing that the block validation at the final time is 3.7 seconds, and there's a throughput is 6,000 transactions a second. So how do you fit 22,000 transactions in a block? Because right now, if I see the block explorer, the transaction I can see is 30, 40. So I think the current usage is 10 transactions a second, right? Current usage is 10 transactions a second.
Oh, current usage.
Yeah.
Yeah. So right.
Yeah.
So internally, we're always testing, much higher levels.
But if you fit from 10 transactions a second, if you fit a 22,000 transaction in a block, from current I can see is 100 transactions in a block, right? So would it reduce the validation time? I mean, would it increase the time of the block validation? Because I mean, I think it is tested in the test net that you are actually putting 22,000 transactions in a block, but right now on a mainnet I can see is 100 transactions in a block, right? So would it increase the time? I mean, you are trying to reduce, which is good, but wouldn't it increase the time if you put a 22,000 transaction in a block?
I didn't fully understand.
6,000 transaction is a throughput. But if you assemble a block in 3.67 seconds, then it means that you are putting the maximum transaction of 22,000 in a block, because that's 3.7 seconds, right? The throughput is 1 second.
Oh, I see. Right.
Yeah.
So you're right. So bigger blocks you're observing on different networks have different finalization times. Yeah, and this is something we're also working on continually improving. On test networks like testnet, there's a vastly different performance characteristic based on how many nodes and the size of those nodes and what their CPU and performance constraints are. And so internally, we test on a lot of different profiles, and this kind of informs our recommendations to validators and node operators for what they should be running. Bigger blocks just need more CPU for more signature validations per second, for example. Higher transaction workloads are going to require just higher TPS means more there's only so many signatures per core you can verify, right? And so the idea that there's some baseline CPU requirements for these higher TPS, either for validating the transactions as they come in or for assembling the blocks, this is going to be observed in different ways on different characteristics and hardware constraints. And so internally, we do test on all different sizes, and certainly with bigger nodes and beefier nodes, you get better numbers there.
But internal verification is typically on the network, which is not very decentralized, right? It is because internal validation is testnet is centralized, right? It's not so when you put 22,000 transaction, propagation delay and propagation through the network, I mean that would cause, I think, immense amount of delays actually. Yeah.
So it depends on what transactions are you actually validating, because every transaction is different.
Yeah.
So that's only a theoretical level.
Yeah, this is what I mean. I mean, it's a theoretical level, yes. 6,000 transaction throughput seems achievable, but putting 22,000 transaction in a block is actually immense amount of work, especially if you have to propagate it to thousands of nodes, validated nodes, right?
Blocks on mainnet have 26,000 transactions. It's not a hypothetical number. Like, these numbers are observed in mainnet, observed on testnet, long-running networks with full blocks at whatever it is, 26,000 transactions a block. So it's not a. We're not saying, hey, theoretically we think it would hit 6,000. We're saying we've observed this in long-running public networks.
It still depends on what the transaction does, because every transaction is different.
Sure. Yeah, absolutely. All tests have characteristics about the test. We also have runtime guardrails. If talked with the last presentation talked about the static bounds, but we've got bounds to make sure that you don't get one transaction that you're on one transaction a second. But yeah, you're right. Yeah.
Yeah, hi, Chris. So I think all these improvements are exciting and make sense. All the directions. Yeah, can you hear now?
Yes.
Yeah, I think all these improvements are exciting and make sense. Different pieces that you're trying to improve. I think my question is about, back to the initial paper and the architecture of distributed system. Some of the fundamental parts of the whole thing. How much you guys are thinking about changing those parts? For example, the architecture of this. So having relay nodes, how different nodes are connecting to each other, or changing more fundamental parts. I'm not sure whether that's something that your team as an engineering part team wants to work on that, or the research team. But it seems that any change there can produce probably much more, result if it's possible. So how much work is being done on, thinking about what parts of the whole, consensus and also particularly distributed architecture can be improved or, fundamentally changed?
So you're referring to the consensus protocol or just the overall?
Anything that comes from the initial design, right? So it can be questioned. There is no reason that that's the final thing or the best thing, right? So of course that was an improvement to anything that existed in the past. But many parts of the design, initial design, there is no final answer that why it should be the best thing, right? It can be theoretically changed or replaced with something better. So so I think that's my question. How long you want to just stick to that design, or how much you are thinking about changing that design?
Yeah, I think there's a lot of changes we've thought about that are sort of radical changes to the consensus protocol itself. The idea of having sort of overlapping consensus traffic and having this idea of pipelining or speculating on the next round. Those are big changes to the consensus protocol that we didn't originally consider. This idea of splitting up the proposals and having them be more optimally forwarded, and a lot of the network routing improvements, I think, might be more closely mapped to what you're describing. This idea of a totally flat architecture, or the idea of a gossip network that is relatively elegant, but could, optimization of the routing itself is like a huge opportunity for us to kind of depart from some of the more, naive gossip traffic forwarding techniques that you might see. There's already some work we've already shipped and currently rely on where nodes are kind of preferring faster nodes, and there's this behavior in the network that optimizes for faster paths, but we can always improve on that and do better, and that's something we're actively researching. A lot of the papers kind of present things in this kind of mathematically abstract way, but since those papers were written, there are a lot of in-practice optimizations and improvements and under-the-hood changes that you might not notice, like the routing improvements that already exist, for example. But yeah, without drilling in on every individual topic, I couldn't speak to like the architecture that you're describing, but I think there is more difference between the abstract sort of mathematical presentation of the Algorand protocol and its implementation than people might be aware of. And maybe that's on us for not documenting it as clearly or making the specs as clear, but I think there's a lot of sort of practical implementation decisions that have been made since then. Thanks.
All right. Well, thank you very much, Chris. Thank you, Noah, as well, for coming up and giving us this wonderful talk about performance and kind of what's been going on.